Right, so 4-5 is called exponential and logarithmic equations and inequalities. So the difference between what we were doing before and what we're going to move into is that these are equations which have an equal sign in them. So you're going to be solving these equations, okay? So you're solving either exponential ones or log equations. So the answers to these are going to be like x equals kind of a thing. So exponential equations would be an equation containing one or more expressions that have a variable as an exponent. And then to solve the exponential equations, the first kind you're going to get is writing them so they have the same base. So if I had something like, God bless you, if I had something like 2, let's make it pretty simple, 2 to the x equals 8. And I wanted to write this to the same base. So how could I rewrite 8 so that it has a base of 2? 2 to the third. So this would be 2 to the x equals 2 to the third. And then this is something called the one-to-one property. When the base is the same, you can just set your exponents equal to each other. So then I would take these two exponents and set them equal to each other, and I'd get x equals 3. So the idea behind that is getting the base to be the same. So if I had, let's say I had 3 to the x plus 4 equals, and again, I'll keep it kind of simple, but let's say it equals 9. So I'm always going to go with a bigger number. I'm not going to try to rewrite 3 so that I could, like 3 would be 9 to the 1/2, but it makes it a lot more complicated. The other way around would be to make 9, rewrite 9 as what? 3 squared. So this would be 3 to the x plus 4 equals 3 squared. And then as soon as the bases are the same, I just grab the exponents and set them equal to each other. So x plus 4 would equal 2, and x would equal -2. So that's the first kind, if one base can be rewritten as the other. The second kind is when you can't do that. So let's say I have 3 to the x equals 5. There's no way to rewrite 5 as 3 to a power, right? Not a whole number, okay? Not even a fraction in this case. So with something like this, then we solve it by taking the log of both sides of the equation. So think about an equation, whatever I do to one side, I have to do to the other. If I'm going to put log in front of 3 to the x, then I'm going to have to put log in front of 5. So we're almost using log as a verb now, okay? So if I were to rewrite that as log 3 to the x equals log 5, think about your properties of expansion. When you've got an exponent on the log, what can I do with that exponent? Move it to the front. So this is, x is going to go to the front. I get x times the log of 3 equals the log of 5. And then if I was going to get that x by itself, how could I do it? Divide both sides by the log of 3. These end up canceling, and then this is where the calculator comes into play. So when you can't get it to change a base, and you have to log both sides of the equation, or find the log of both sides of the equation, then you're going to use your calculator. And I would simply type in log of 5, make sure you close your parentheses, divided by log of 3. And I get x equals 1.464, or 1.46. Could I check this? How? My original thing was 3 to the x equals 5. So if I'm saying that x is 1.46, then if I use my calculator to raise 3 to the 1.46, I should get an answer pretty close to 5. Now we've rounded, so it might not be exact, but when I type that in, I get 4.97. So it's pretty close. Again, rounding won't make it exact, but at least I'm pretty close. So those are the two types that you're going to see with exponential. One where you can change the base to be the same number, and you would just change the base, use the one-to-one property. And the second where you can't, and so you have to find the log of each side of the equation. All right, so try it. So it's a little bit trickier because I can't change just one of these, right? I can't make 9 raised to the power to get to 27. If one side was 3 and one side was 27, I could do that. But they both need to be changed. So I could change 9 to be 3 to the second power, but that's still being raised to the 8 minus x. And then I can change 27 to be 3 to what power? Good, 3 to the third, and that's still being raised to the x minus 3. So what do you do when you raise a power to a power? What happens with those exponents?
Add.
Nope, multiply, good. So I'm going to multiply these. So I'd get 3, 2 times 8, which is 16, minus 2 times x, negative 2x, equals 3, and I'm going to multiply these. 3 times x, which is 3x, 3 times negative 3, which is minus 9. So this time we had to change both sides. Are the bases the same now?
Yes.
So I can just grab my exponents and say that 16 minus 2x equals 3x minus 9. And solve for x. So add the 2x. And then add the 9. And divide by 5. And then just like before, I can plug these back in here to check. So 9 to the 8 minus 5 should equal 27 to the 8, or sorry, 5 minus 3. 9 to the 4th, 9 to the 3rd should equal, that's 27. 27 to the second power. And if I use my calculator to check both those answers, the left side should equal the right. Isabel.
So like the objective is to make like a 15 try to make both of the bases the same.
Correct. And there's going to be times when you can, and that's when you can do the one-to-one like we just did. And then there's going to be time when you can't, and that's when you're going to log, which is the next one. Okay? So again, it says solve and check. Now I've got 4 on the left and 5 on the right. Any way to make one become the other? No. So I'm going to take the log of both sides of this equation. So log of 4 to the x minus 1 equals log of 5. What do I do with that exponent? Bring it to the front. Then what? Good. Divide by log of 4. And then add 1. Perfect. Add the 1. So you could have divided like log of 5 divided by log of 4 and then added the 1, or you can wait and do that all in the calculator. So log of 5 divided by log of 4 plus 1, and I get x equals 2.16. With me so far? Yeah? And then to check it, I'm going to take it and plug it in. So 4 to the 2.16 minus 1 equals 5, or 4 to the 1.16 should equal 5. And then use your calculator to check that. 4 to the 1.16, and I get 4.9933 and so on, which is pretty close to 5. Ian?
So like at what point do you know that you routed correctly if it's like close enough to the answer?
I would say as long as you're within 1/10. So as long as it's like a 0.9, if it's going to be a 5, that kind of thing.
Okay.
Yeah.
When I put it back in, does it work for you?
All right, so can I make 15 2 to the power of something? No, right? So this is going to be the one where I'm going to take the log of both sides. So log of 2 to the 3x equals log of 15. Bring the exponent forward, 3x. Log of 2 equals log of 15. Okay, I can either divide first by log of 2, and then I end up with 3x equals log of 15 divided by log of 12, and I can keep it that way, and then if I wanted to get that x by itself, I'm going to do what? Divide by 3. So I can do that. I can round the log of 15 divided by the log of 2 and take that divided by 3. Or if it's straight multiplication again, across, you can actually do that all in one step. So I can do log of 15 divided by 3 times the log of 2. But you would want to group these together in parentheses. So I can either do it in 2 steps. Find the log of 15, divide it by the log of 2, and then divide that by 3. I get 1.302. Or I can do the log of 15. Make sure you close your parentheses. Divided by, open parentheses, log of 2 times 3. Close your parentheses. Either way, you end up with 1.30229 and so on and so forth.
Is it okay that we did the log of 15 over log of 2, that over 3?
Yeah.
Okay.
Yeah, you should get the same answer. So then again, when you're plugging back in to check, if I take this and plug it back here, 2 to the 3 times 1.3, or 2 to the 3.9 should give me pretty close to, if not exactly, 15. Okay. 2 to the 3.9 is 14.92. Raise your hand if you got that one right. Okay, questions on it? Okay, then you're going to get log equations. So in those equations, there was no word log. We took the log to solve them, but the initial equations didn't have the word log. Now we're going to have the word log actually in the equations. And there's 2 different kinds. One in which log is on both sides of the equation. So if I've got a log equation, which is a log expression, or an equation that involves logarithmic expressions that contain a variable, then you can solve log equations by using the properties of logs. So this also can be used in the one-to-one property. So if I have the log of the same base on either side of the equal sign, if I had log base 3 of x equals log base 3 of 5x plus 1, something like that, then as long as these match, it's just like having an exponential equation with the same base. I can grab whatever's next to it and set them equal to each other. So it's the same one-to-one property, it's just that this time you're using logs. And then I would solve this equation. I would subtract the 5x, negative 4x equals 1, and then divide both sides by negative 4. Bad example because you end up with a negative, but you can kind of get the idea. So if you have the same log, or a log with the same base on either side of the equal sign, then you just take whatever's next to that log and set them equal to each other. So you're using the one-to-one property with logs instead of exponents. That's the only difference. The other kind is like this. Now there's only one log on the other side of the equal sign, right? There's one log and then the other side has no logs. So to do this, you want to get this expression into exponential expression. So how do I change when it was, let's just say it's log base 6 of x equals 1, for example, before we even get to the 2x minus 1. God bless you. If I asked you to put that into exponential notation, how do you do it?
6 to the power of 1 x.
Good. So the little number member comes over, picks up the one that's on the other side, and drops off, leaving the number that was next to the log by itself. So I'm going to do the same thing here. The 6 comes over, picks up the negative 1, and then drops off, and I get 2x minus 1. Ian?
Can you explain why you moved the x between the 6?
So this is if there's only one log. If there's only one log, there's no one-to-one property, right? There's no log on the right side of this equation. And the only way to get rid of that log is to put it into exponential notation.
Oh, that's usually you moved that thing that you took.
And now we got rid of the log. So what is 6 to the, what is 6 to the negative 1?
1 over.
Good. Then what? Add the 1, so I get 1 and 1/6. Good. And then divide by 2, which is the same thing as multiplying by a half. So I can convert this into improper fraction. 6 times 1 is 6, plus 1 is 7/6, divided by 2, which is the same thing as 7/6 times a half. And I get 7/12. Most likely you'll have a calculator on this part of your test. It's still in the works, okay? But if not, then that's how you do it. If you did have a calculator, then you can make that 1/6 a decimal, add the 1, divide by 2, same thing, okay? So if I had it in decimal format, that would be 7 divided by 12. That would be 0.58333. And then again, just like before, check it by plugging it in. So log base 6 of 2 times 0.58 minus 1 should equal negative 1. So then 2 times 0.58 is 1.16. Log base 6 of 0.16 equals negative 1. And this time I would have to use that change of base. Change of base tells me if I want to figure out what this is, that I do log of 0.16 over log of 6. And I get negative 0.10227, which is again rounded but pretty close to negative 1. So I think the hardest part of logs is looking at it to start with and trying to figure out which approach I'm taking. So start to ask yourself the same kind of questions. Is there a log on either side of the equal sign? If there is, you're probably going to use the one-to-one property, which is that one we did just before this. If there's only one log, then you're getting it into exponential notation, like we did. Take the little base, come over, pick up the guy on the other side, and then solve it. If there are 2 logs on one side of the equal sign, then I have to condense them. Yep, so the good thing is this is forcing you to review your other properties of logs, okay? But obviously they get more complicated. So if I have log base 4 of 100 minus log base 4 of x plus 1, how do I condense that so there's 1 log on the left-hand side? Good. So remember, when you condense subtraction, it becomes division. Now I have 1 log on the left-hand side, which means I want to get us into exponential notation. So the 4. Go ahead, Brian. Good. And 4 to the first is 4. I would look at this 2 ways. One is you could multiply times x plus 1. So the one way I would approach this, and you have to see which one makes more sense to you, is multiply by x plus 1 here and here. I'd get 4 times x plus 1 equals 100. Distribute. Actually, I could divide there. I didn't have to distribute. Subtract the 4. And then divide by 4. The other way is if you're better at seeing this as a proportion. So 4 equals 100 over x plus 1. Then put that 4 over 1 and cross multiply. So 100 times 1 is still 100. 4 times x plus 1. And then I can divide both sides by 4. And then subtract the 1. So if you see one fraction on either side of the equal sign and you'd prefer a cross multiplication, then I would set it up the way that the second one is. Just put that 4 over 1. If I've got one number on one side and a fraction on the other, just put that 4 over 1 and then cross multiply and solve it that way. Questions on that one? All right, so